time, a mysterious force that shapes our lives, influences our decisions, and leaves a lasting impression on everything we do. But what is time? Is it truly an independent entity, or is it simply a human mind construct to make sense of the ever-changing flow of life? This is the question we intend to investigate on this fascinating journey through the lens of Einstein's theory. Philosophers, scientists, and poets have been attempting to solve the mystery of time since antiquity. For some, time is a relentless arrow that moves inexorably from the past to the future, whereas others see it as an illusion caused by our limited perception. However, Albert Einstein's genius shed new and powerful light on this issue, permanently altering our understanding of the universe. Einstein proposed that time is relative rather than absolute, a revolutionary concept that calls into question our most fundamental assumptions about the nature of time and space. On this journey, we will look at the implications of this radical viewpoint, from the fundamentals of relativity to the most profound implications for our understanding of the universe and ourselves. We are taught from childhood to think of time as a straight line that connects the past and future with an ephemeral present that moves relentlessly forward. This is our intuitive understanding of time, which is deeply rooted in our collective psyche and informed by our daily experiences. However, this simple view conceals a surprising complexity that only becomes apparent when we examine it more closely. To better understand this intuitive concept of time, consider the movement of celestial bodies in the sky. The sun rises and sets, seasons change, and the passage of time appears to be inextricably linked to these cyclical events. However, the idea of time as a continuous and uniform progression is an illusion, a convenient simplification that obscures the true nature of time and space. Our intuitive understanding of time is also influenced by our subjective experiences with the world. When we are happy, time seems to fly by. When we are bored, it drags on indefinitely. This variable perception of time implies that the passage of time is a subjective construct that differs from person to person and situation to situation. Albert Einstein proposed the theory of relativity at the turn of the 20th century, and it transformed our understanding of the universe forever. This theory, which was divided into two parts, the special theory of relativity and the general theory of relativity, provided a new framework for understanding space, time, and gravity. Einstein's relativity tests our most fundamental assumptions, but it also provides a more comprehensive and integrated view of the universe. The special theory of relativity, proposed in 1905, states that the laws of physics apply to all observers moving at constant speed. This means that there is no absolute time that is the same for everyone, but rather that time is relative and varies with the observer's speed. This innovative theory sparked a slew of unexpected discoveries, including time dilation and length contraction, that call into question our basic assumptions about physical reality. Einstein's general theory of relativity, developed in 1915, contributed to our understanding of the world by proposing that gravity is a manifestation of the curvature of space-time induced by the presence of mass and energy. This unified view of space and time fundamentally altered our understanding of gravity, turning it from a mysterious force to a natural result of the universe's geometry. The general theory of relativity described gravity as a curvature of space-time, providing an elegant and simple explanation for a variety of observed phenomena such as planet orbits, light deflection, and black hole formation. Consider a massive clock, as large as the universe itself, marking the unending rhythm of time's passage. This is the clock of the universe, a fascinating metaphor that asks us to consider the meaning of time on a cosmic scale. Einstein's theory of relativity states that time is a dynamic dimension that can be changed and warped by the presence of mass and energy. This transformative perspective encourages us to reconsider our understanding of time as a straight and unchanging line, and it challenges us to see time as an intrinsic element of the universe's structure. The clock of the universe reminds us that time is more than an abstract measure. It is a fundamental characteristic of the universe, as real and tactile as the place we live in. Physical items can modify the geometry of space, and they can also affect the passage of time, resulting in a close relationship between space, time, and matter. This unified picture of space-time encourages us to consider the world as a whole, with each component inextricably linked to the others in a cosmic dance of forces and energies. In our everyday lives, we tend to think of the now as an absolute and universally true instant that applies to all observers. However, according to the theory of relativity, simultaneity, or the idea of events, happening at the same moment is relative and can change based on the observer's movement. This means that what is now for one observer may not be now for another, who is moving in relation to him. This difficult concept was clearly depicted in Einstein's famous thought experiment known as the twin paradox. In this experiment, one of the twins goes on a high-speed spaceflight while the other stays on Earth. According to Einstein's relativity, the traveling twin will see time differently than the twin who remains on Earth due to time dilation produced by their relative speeds. When the traveling twin returns to Earth, he realizes that his sibling has aged faster than him, despite being born at the same time. This perplexing conundrum clearly demonstrates the relativity of time and calls into question our most fundamental assumptions about the nature of reality. According to relativity theory, space and time are components of a single phenomenon known as SpaceTime. This innovative viewpoint encourages us to reassess our understanding of the world as a static collection of objects in space, instead challenging us to perceive the cosmos as a dynamic web of interrelated events in which space and time are intimately linked. This unified perspective on space-time implies that the cosmos is a dynamic and ever-changing entity, with one component interrelated and influencing the others. Just as mass and energy affect the geometry of space, the distribution of matter in the universe shapes time, resulting in a complex network of influences that define the trajectory of all cosmic events. Einstein devised a series of thought experiments to convey the complicated concepts of relativity in an understandable fashion, challenging common intuitions about the structure of time and space. One of these thought experiments concerns the light clock, an imaginary device that explains how light and time are intrinsically linked. Consider a clock made out of two perfectly mirrored mirrors positioned face to face, with a ray of light passing between them. For an observer at rest in relation to the clock, the time it takes for light to go from one mirror to the other is simply the time it takes for the light to travel that distance. However, for an observer moving relative to the clock, the path of the light will be longer due to the clock's motion, resulting in a perceived time dilation. This simple thought experiment effectively shows the essential principle of Einstein's relativity, which states that time is relative and can vary based on the observer's motion. One of the most exciting features of relativity theory is time dilation, a phenomenon that calls into question our ordinary understanding of time. According to relativity, time passes more slowly for a traveling observer than for a stationary observer, an effect that is more noticeable as the observer's speed approaches the speed of light. A number of scientific tests, including the well-known time verification experiment using high-precision atomic clocks, have validated this remarkable occurrence. In these studies, Scientists mounted atomic clocks on high-speed airplanes and compared their timing to clocks at rest on Earth. They discovered that moving clocks mark time more slowly than stationary clocks, validating the theory of relativity. This temporal dilation has significant practical implications, particularly for space explorers traveling at speeds approaching the speed of light. Time would move more slowly for these cosmic explorers than it does for Earth observers, allowing them to traverse over cosmic distances in a relatively short period of time. This phenomena, known as the twin paradox, calls into question our long-held beliefs about time and reminds us that the cosmos is far wilder and more wonderful than we could have imagined. Gravity, in addition to speed, has a substantial influence on the passage of time, according to relativistic theory. Einstein proposed that the existence of mass and energy generates a curvature in space-time, which can result in time dilation in locations with higher gravity. This means that time moves slower in areas with high gravity, such as near a black hole, than in areas with low gravity, such as the Earth's surface. A striking example of this phenomenon is an experiment with atomic clocks positioned at various heights on Earth. Scientists discovered that clocks at higher elevations indicated time somewhat faster than clocks at sea level, owing to variations in gravity intensity between these places. This astounding discovery validates the theory of relativity's prediction and reveals how gravity may have a physical and observable effect on the passage of time. One of the most fascinating elements of the theory of relativity is the contradiction that time moves slower for moving objects than for stationary observers. This concept calls into question our basic understanding of time and the basis of physical reality. To better comprehend this phenomenon, we can resort to Einstein's famous thought experiment with twins, in which one of the twins travels in a spaceship at fast speed while the other remains on Earth. According to Einstein's theory of relativity, the twin who travels across space will perceive time more slowly than the twin who remains on Earth due to time dilation produced by their relative speeds. When the space-traveling twin returns to Earth, he realizes that his sibling has aged faster than him, despite being born at the same time. This interesting contradiction vividly demonstrates the relativity of time and forces us to reconsider our assumptions about the nature of reality. One of the most severe examples of Einstein's relativity is black holes, which are cosmic objects so dense that nothing, not even light, can escape their gravitational pull. Black holes are enormous distortions in the fabric of space-time, where gravity creates such profound curvature that nothing can escape its unrelenting embrace. For an observer outside a black hole, time appears to move more slowly as he approaches the event horizon, the point beyond which nothing can escape. Gravitational time dilation is a direct result of the severe bending of space-time generated by the presence of a black hole. Thus, while time appears to pass normally to a distant observer, it appears to slow down increasingly as one approaches the event horizon, eventually coming to a halt. These are some of the most fascinating features of Einstein's theory of relativity and its application to our understanding of time and space. From time dilation to the effect of gravity, relativity forces us to reconsider our understanding of the nature of reality and urges us to explore the depths of the cosmos in search of answers to the universe's riddles. One of the most intriguing ideas to come from the theory of relativity is the concept of time travel. Although popularized in science fiction, the actual possibility of traveling to the past or future is dubious and the topic of numerous scientific arguments and conflicts. According to relativity, it is theoretically feasible to travel across time, but there are various constraints and problems that make this concept extremely difficult to implement in practice. One of these issues is the so-called grandfather paradox, which occurs when someone travels back in time and takes an action that modifies the path of events in such a way that they no longer exist. For example, if someone came back in time and prevented their grandparents from meeting, it would result in a contradiction because that person would no longer exist to execute that action. These paradoxes complicate the idea of time travel while also raising fundamental questions about the structure of time and causality. One of the most intriguing parts of relativity is the topic of simultaneity and the notion of the now. According to relativity theory, what is now for one observer may not be now for another observer who is moving in relation to him. This implies that there is no globally valid moment that is the same for all observers, questioning our assumptions about the nature of time. This notion raises serious problems concerning the nature of reality and awareness. What implications does the fact that time is relative and the now is a subjective construct have for our understanding of existence and human experience? These are profound philosophical concerns that call into question the distinctions between science and metaphysics, as well as our understanding of the nature of time and reality. One of the most intriguing consequences of relativity is that time is not a static and autonomous object, but rather a dynamic dimension that may be influenced and deformed by mass and energy. This indicates that time is not a straight and unchanging line, but rather a complicated network of interlinked events, with the past, present, and future inextricably intertwined in a cosmic dance of forces and energies. This non-linear perspective on time challenges our traditional understanding of time as a continuous march from the past to the future, instead inviting us to consider time as a fluid and ever-changing dimension. In this view, time is no longer an abstract measure but rather an intrinsic element of the universe's structure, a living and throbbing dimension that shapes and is shaped by every cosmic event. According to relativity, time is more than just an independent dimension. It is an important element of a greater reality known as SpaceTime. This means that time is as real and physical as the three dimensions of space we occupy, and when combined, they constitute a coherent structure that dictates how the universe works. This new viewpoint challenges us to reconsider our understanding of time as an abstract entity, leading us to see time as a physical dimension that can be explored and comprehended in the same way that space is. Under this light, time ceases to be a mysterious entity and becomes an essential component of physical reality, a dynamic dimension that shapes and is shaped by the presence of mass and energy in the cosmos. This paradigm shift requires us to broaden our understanding of the nature of time and explore the depths of the cosmos in order to gain a more complete picture of the world. The theory of relativity also provides an intriguing viewpoint on the arrow of time, or the direction in which time flows. While our intuition tells us that time moves inexorably from the past to the future, physics explains that this is regulated by the second law of thermodynamics, which states that the universe's entropy, or disorder, always grows throughout time. This theory proposes that the direction of time is inextricably related to the direction of entropy, implying that time moves from the past, where entropy is low, to the future, where entropy is high. This leads us to understand time not simply as an abstract dimension, but as an important aspect of the universe's dynamics, with the evolution of time inextricably tied to that of entropy. Aside from its physical nature, time has a fundamental psychological dimension that shapes our perception and experience of the world. Philosophers and thinkers have discussed the nature of time and its impact on human awareness since antiquity, but relativity theory provides a fresh viewpoint on the subject. According to relativity, our sense of time is influenced by how we interact with the space-time surrounding us. This means that time is not an objective metric, but rather a subjective construct that fluctuates from person to person and situation to scenario. Our perception of time is influenced by a number of elements, including our speed, position in space, and relationship with gravity. Thus, there is no single, correct way to perceive time. The theory of relativity may appear remote and abstract, but it has practical and tangible implications in our daily lives. A clear example is the Global Positioning System, GPS, which employs relativity principles to precisely position things on Earth. We bring you an incredible series of videos like this one. Subscribe to our channel so you don't miss out. Because of the time dilation predicted by relativity theory, GPS satellite clocks run slightly quicker than clocks on Earth's surface. This occurs because the satellites travel at fast speeds and have a smaller gravitational force than the Earth. If not for this relativistic adjustment, GPS signals would become inaccurate in minutes, rendering the system unsuitable for precision navigation. These are just a few examples of how Einstein's theory of relativity affects our current world, including GPS technology, space communications, and much more. These practical applications remind us that fundamental research may have tangible and profound repercussions in our daily lives, and they inspire us to continue studying the world in pursuit of new discoveries and inventions.